Very loudly. Okay, can everybody hear me? Okay, good. All right, so thank you very much for coming to the IMA Public Lecture. My name is Fadil Santosa. I'm the director of the IMA. I'm very pleased to introduce tonight's speaker, Dr. Carrie Grimes from Google. I think everyone in this room has heard of Google. Okay, good. Dr. Grimes studied anthropology at Harvard University, where she did research on Mayan settlement patterns in Honduras. While doing her work, she realized that she was drawn to the more data analytic aspects of her study. When she graduated in 1998, she decided to pursue a PhD in statistics at Stanford University. At Stanford, she worked with David Donahoe, who is considered one of the brightest minds of our generation. Carrie's thesis dealt with high-dimensional data, especially on methods for dimensional reduction. She finished in 2003 and joined Google upon graduation. At Google, as data scientist, she uses statistical methods to help improve the company's search technology. The job title is Principal Engineer at Google's Data Analysis and Algorithms and Search Infrastructure. Dr. Grimes is author of many important research articles on data analysis and web search. The talk tonight is entitled Keeping Track of the Web, Modeling Information Growth. So please give a warm welcome to Dr. Grimes.
Hello. Hopefully you can hear me. It sounds about right. I'm getting told it needs to be a little bit louder. This is always the exciting part of the talk.
It works. It's working.
Any better?
Yes.
A little bit? Still? Needs to be more. Let's do it here. Okay. No, too much. How about here? That's good? All right, it's hard for me to tell. All right, so I'm here to talk a little bit about the internet and a little bit about the web, and then I'm also going to talk about a particular problem that I've worked on. And at the very end, we'll get into some more kind of theoretical stuff, but I was told this was supposed to be relatively accessible, and I think this is kind of a fun example of the kind of work that you can do using kind of basic probability and how some of the stuff that turns up in these textbooks actually applies when you get to working in the real world. I also think it's an interesting question because we'll talk about statistical models that were really invented for other applications and how somehow the web is kind of organic enough that they really apply in this context. So let's spend the first part of the talk talking a little bit about search engines. So most people, when they type things into Google, they don't necessarily think about what happens next, right? So you're looking for pages about Justin Bieber getting arrested. How does Google actually find those pages? And the answer is that this is how the original term of crawling the web came about, that the web is represented by my little diagrams here, consists of a bunch of sort of hubs. They can be at the domain level or the host level. And traditionally, they were really universities, right? And they each link, and each one of those arrows pointing outward from a big colored dot is called an outlink. And in-link means that someone links to you. So in some cases, those arrows are bidirectional, and in some cases, they're single directional. And the way that a search engine would start back in, I don't know, 1991 or something, is that you would pick a text-based page, usually on a university system, and you would then just follow all the links from that page in some order, and then you would look at the list of links that you found on the new pages when you actually process them, and then you would go to all of those pages and download them. And that's what was called spidering the web, right? So you're spidering, you're walking around, and it became known as crawling the web. And traditionally, this was all text-based, it centered around university domains, so there were some particular characteristics of that we'll talk about in a minute. But what actually happens is that a search engine indexes the content on that page. So the search engine looks at the content of the page, downloads the text traditionally, and computes things like keywords and number of occurrences of words, and creates a record which is stored in an index, much like an old-style card catalog was stored. that can be quickly accessed as a user types a query, right? So there's some whole computer science design that goes around how you structure that index, but the main idea is that this stuff is pre-computed, right? And so you create an offline repository. You basically take the web, you take everything that you're downloading from the web, probably 24 hours a day, you push it through what's called indexing, and indexing both extracts key terms and phrases, right? So you want to know, what is this document about? And you would do that by, say, counting the number of times the word, Justin appeared, the word Bieber appeared, the number of times those two words occurred together. And then you would also attach any other meta information to the page that you wanted. For example, what language it's in, what country you think the domain that it's on is in, anything else you might know about it, like does it seem really spammy, is it a high quality site, any other signals that you might have about the page, right? And so all of this stuff is stored in what we call a web index. And when a user types a query, the search engine isn't going out and getting the page right then. It's using what it's got stored in the index to quickly decide which pages are relevant for your query. So how do you pick the best pages, right? This is the critical question for a search engine. So in order to talk about how all this came about, I'll talk about pre-Google search engines, right? They use traditional information retrieval techniques. And there's a whole science to this, but typically those come down to counting the occurrences of a particular word and something called the inverse document frequency, which means how common is this among all the words in the document. So if you have a really long document, it may have a lot of words in it. So a word may be a rare word, but it may be only one of many words that occur in that document. So typically this is how old school retrieval functioned. This was how like a linguist would talk about retrieving a page from a text corpus. This is how a lot of the kind of library terminal-based retrieval worked. They would have pre-indexed keywords and things like that. You would also, for example, weight words by position on the page. So near the top would be better. In the title would be good. In an HTML page, you have information about what the title is. And you also might do something like recognize natural language behaviors. So some of the original search engines would actually try to parse content in a very linguistic way. What happened? Well, they got spammed extremely badly. And the most common thing that you would see is keyword stuffing. So that's where if you created a page that was effectively an advertisement for a product, you would just repeat the same words over and over and over again, like t-shirts, and you'd have all the misspellings, and you'd have like 100 repetitions because this whole term frequency thing would get sort of overwhelmed by that. And then your page would always be really, really topical for t-shirts, right? And get ranked above the Gap or whatever else. The other thing, and this was my real favorite when I started at Google, because this was still a battle that was being fought at Google in 2003, is you would, for whatever reason, basically try to stomp on a legitimate news topic or have your pages show up for like the Canadian Prime Minister's name. And the way you would do this is by having a computer-generated natural language story that was full, that looked like language, and you would just stuff the person's name, everywhere in there. This was also a very, very common way to get porn listed in the search results by writing what was effectively a story, and then basically it would turn up for the Canadian Prime Minister's name, except it was actually a porn story, right? And it looked like natural language to all of the processors, but it would be in the search results. And when I first worked at Google, Matt Cutts, who you sometimes see giving talks, there was a lot of work on making safe search work, right? Because there's a lot of stuff on the internet that people don't want their high school students looking at in the library, for example. And this was a big thing, right? To basically think of ways, and his wife would bake cookies, and he would reward you if you could find something that would beat one of his filters to actually keep this stuff out. You know, it was a different era. But what the big kind of issue then was that all of these kind of terminological things, they don't have any reputation weight, right? Smart people can construct pages for commercial purposes because it entertains them, whatever. That really defeated some of this term frequency work. And today, 10 years later or so, it's actually an even bigger issue, and the reason is that the content on the web has really changed from that traditional model of text to short pieces of text where natural language processing doesn't work well, like tweets, Facebook postings, images, videos, and none of those things have this kind of term frequency behavior, right? You might have a great image of yourself, but it's got your name on it once, if you're lucky, and it's in the caption. So none of this is going to work, right? And so the big thing that came about when we start to talk about Google and how search works is that they started to build signals about reputation. So the big kind of innovation that came from what Larry and Sergey were doing initially was this idea called PageRank. So if we go back to my sort of picture of the web, what PageRank does is it gives the probability that a random web surfer will be at each page, and it ticks the clock forward. So we look at the node labeled A, and A has 3 outlinks. One of them goes to the page we're interested in, which is page P. And these are all the pages on the web in our example. And what we do is we say that with probability B, a surfer on the page A will jump along one of any of the outlinks. So if it has 3 outlinks, then the probability is B over 3, basically. And then with probability 1 minus B, where B is some small amount, the surfer goes to some random page on the web. And so if we look at what the PageRank and PageRank computes these things simultaneously over the web graph. So if we look at the PageRank of P, which we're interested in our example, it's our probability B, which you get called a damping factor in some of the academic literature, times 1 over 3, because there's 3 outlinks from A, times the PageRank of A, and then 1 over 2, because there's 2 outlinks from B, times the PageRank of B. And then there's some number for the chance that you've gone to a random page. So you basically start with what we call a seed. This was the traditional PageRank model, so your seed was probably Stanford or, I don't know, the University of Michigan or something like that. Because this is, predates me at Google. This is a long time ago. And you basically give them a sort of PageRank initialization value. There's a lot of ways to do it. And then you just calculate forward, right? So you're basically transferring the reputation of any of the hubs that you start with onto the pages that are connected to them, on the principle that if a page connects to a reputable source, it's more likely to be a reputable page. And it turned out that this was much harder for people to actually spam because it took a lot of work to build up that kind of reputation on the web. When you look at something like a university, it would be orders of magnitude higher in PageRank than even a small commercial site, much less a site that someone set up yesterday to try to get views for their ad or a new product or something like that. So this was kind of the big change, this idea of reputation-based signals that were query independent. That came about when Google first started doing this. And this is important when we talk about what we're going to talk about today, which is updates. Because if you think about the shape of that graph, you have to keep following the graph and know what the web graph looks like in order to compute these reputation-based signals, right? So one of the things I want to talk about today is, or the primary thing, is how do we actually keep track of all of the updates that occur on the web and all the information changes? And there's sort of a couple of major reasons for this. The first is that content obviously changes. So if you run a blog, you write a new blog post about a different topic, you want that to show up in people's searches. And we just talked about how the index is pre-computed, right? So if that computation, if they don't have a current copy of your page, when that computation occurs, you can write a whole new posting about the most major news article ever, and Google won't know about it, right? So we've got to make sure that we get the actual content from that page and extract the keywords. The second thing is that it's important to infer timeliness, right? So there are certain words and phrases that might not mean the same thing today as they did last year or even 5 years ago. And they're phrases that are sort of introduced into discussion because a news event occurs or something like that, and you want to make sure that you're not confusing a current natural disaster with one from 2 years ago, right? So when you index the page, you want to have a good sense of what current topics are. There's also the issue of link changes, that there's no enumeration of the web, so if links to new content are created, we don't know about them until we crawl the page with the link. And the final thing is signal propagation, as we just talked about with PageRank. There's all kinds of information you can propagate along the graph, like PageRank is, or that you can extract from the graph. And none of that's available to you if you don't know about the current structure of the pages. So let's talk about strict content change. So this is a good example of a page. I think they try to find homes for puppies and different pets, and it changes fairly often. The center section of it has postings from people, so on and so forth. So this is a simple example of a case where you have to recrawl this page to try to get information about, someone who's looking to buy a Weimaraner puppy in Minneapolis this month needs the most current postings that are available online, right? So this is the simplest example. The other critical thing, as I just said, is adding new content. And typically content comes in bundles, right? So if we have our web graph and someone creates a new page that links into the Blue Hub, and that has a whole set of children pages, maybe it's a new course, it has a syllabus, it has links to textbooks, related content, they'll sort of create this whole universe. And the only way that we know that that universe exists, because there's no notification, is that we crawl and reprocess the page that contains the sort of main link to that content. And so it's really critical that we be able to pick up pages quickly after they have a change, a creation, especially a link that's added. So here's a good example of that. These are sort of state parks pages, and they have different postings about things that are of interest. They've often just written these things that are of interest, so nobody else on the web is really linking to them. And so if you don't keep recrawling this page, you actually don't have a direct link on Google to whatever their latest conservation plan is. Sometimes this contains like trail closures, other things like that. So this is the kind of example of a link that you want to pick up. There's new stuff that happens. This is an interesting example from right near my house last week. Someone told me there's a new coffee shop that's like a block from us, and I didn't know that it was actually open. And on the right, we have even user-submitted or reviewed links. And on the left, we have what's actually appeared on the web. And I think I took this the day this was created. And the web has actually caught up. They know that this coffee place is now open in the Castro. But the listings, even though they're automatically updated, they're still 24 hours behind, and they only have the address for the old location of the coffee shop, right? So it's something where it's really important to people to be able to use search engines to find kind of data on current events, and even something small like this, usually people, and I expect to be able to use the internet to pick up, openings, closing, things like that. So this is just a common example of where, human curated listings, even with, just like a 24-hour turnaround, are slower. This is a fun one. This used to be a Tour de France example, but it was too out of date these days. One of the things you can see, and you can actually play with this yourself if you go to Google Trends, you can create these relative frequencies of different queries and different phrases. So this is the relative frequency of Bitcoin. You can see it comes in 2011. There's a big jump at letter G where it comes in. But actually, there's a little jump at F. It's hard to see on the projector. But what it is that there was a Good Wife episode about Bitcoin. And it was actually called something like, "What is Bitcoin?" or something like that. So there were a bunch of people who were typing this question, which Google typically interprets to be like, "I want a definition of Bitcoin." But they were actually talking about the name of it. They were trying to get the name of this episode right. And then in E, there was a heist on Bitcoin, and there's a peak right there. It was closed down because someone was actually coming up with a way to create fake Bitcoin. I mean, how do you steal it anyway? But leaving aside the existential issues, we then have the 2 Bitcoin crashes. And one of the things that's important is that, Google indexes a lot of information from these pages, but one of the things you need to understand is the kind of relative importance of phrases, right? So a new phrase may not be that common on the web, but if you start to see it in a query stream like this, you need to understand that it may actually have a different meaning, that it's a phrase you need to create an index record for, even if it wasn't something that would have made it over the cutoff previously, right? So having more current information, even when you're indexing the same copy of the phrase, the same copy of a page can be very useful. So the other issue here, and we started to get into this with PageRank, is that PageRank isn't really the only signal that you can get from the web graph. And here, this is just a snapshot from something I'm going to show you later, but this actually shows the relative link structure from an old copy of our PageRank graph of different languages. And although it's something you might have been able to figure out on your own, it's a good example of why looking at these connections is important. So the circles are colored by language family, and the strength of the gray links is the sort of relative interconnectedness of these two things. And we're going to see an example in a minute of one that's not a great measurement. But you can see basically in red, Spanish, the size is the number of pages, relatively speaking. You can see Spanish being connected to Basque, which is a different language family, and to Catalan, which is considered the same, Galician, and then over to Portuguese. And you can also see the sort of European connections to Italian and French, and some other languages like Occitan, I think is the right term, but it's a French dialect or an old one. And then you can see Esperanto over here, which also connects into Polish. So you get actually a lot of information, and sometimes you see strange connections, like there's an Indian language in the middle here, and it's actually because of the French. There's a strong French connection. There's a community of sort of expatriates there who generate a lot of stuff. So this is a case where you really see unrelated languages, but the populations have something geographically common. But there's all kinds of things that you can use this graph for, and so it's important to have a pretty current idea of where individual pages are. And then I have a reminder I'm supposed to show the video. So typically I show this graphic online, but I've had some poor experiences with connectedness. So this is a larger version of what you were just looking at. And you can see that if you actually pull on this graph, as I'm about to do in the video up there on Swedish and Norwegian, you can see how these languages all move together. And you've got Danish and you've got Faroese, which is an island between Denmark and sort of Iceland or the rest of Scandinavia. And then over here you see stuff that you expect, like there's traditional Chinese, Japanese, Uyghur, which is an ethnic language. But then you also see this big, fat Japanese to Yoruba connection, which doesn't make a lot of sense until you look at the web and there's this one guy who is convinced, yeah, and then English, if you connect English, because it was disconnected before, it just eats the whole graph and like pulls it into the graph. There's this one guy who, and this is from some years ago, but he believed very strongly that Yoruba and Japanese should be related languages. And so he wrote a whole site which has all these joint links. And because there's not a lot of, like, Africa in general doesn't have a very strong web presence per capita, and so there's not a lot of content in Yoruba. And so when you normalize this graph, it looks like this huge link because it is actually a significant portion of the links that go into pages that are in Yoruba are connected to Japanese pages. But it's partly because this guy's doing a comparative linguistics study, and he feels very strongly that these two languages actually have a lot of similarities. So it creates, because the web is so small in one of the languages, it creates like a fake, a heavy graph link. So that's always one of the dangers of doing this stuff. And I think that, you know, a lot of the recent analysis that's done tries to be much more sophisticated about how to actually follow this graph and what data should be kind of pushed along it and what shouldn't be. But I think it's kind of a fun example to get you thinking about, you know, what's possible from the web. All right, let's see if I can transition back. So we care about updates, but we can't crawl everything all the time. So here's a simple example. Let's say that the average document size in a corpus that you want to crawl of documents, and this varies a lot depending on what they are, is about 20 kilobytes. That's fair. Now, once you get through the idea of attaching metadata about other things, it could be much, much larger, or you could make it much smaller if you were looking at short documents. But it's fair. If you have to crawl 1 billion documents, that's about 20 terabytes of data. So anyone know how big the disk on their home computer is? Yes?
I think it's like 1 terabyte maybe?
Yeah. So right now, like, you get 1 terabyte disks, and I think if you have a flash, like if you buy a new MacBook Air, it's like 128 gigabytes, which is less. So a terabyte is 10 to the 12, and I think a gigabyte is 10 to the 9. Yes. I always get this wrong in public, and it's embarrassing. And a home internet connection, you might be looking at maybe 2 megabits per second. So keep in mind these are bits and not bytes, and a bit is usually about 1/8 of a byte, right? So if you have a 1 megabit per second home internet connection, you have about 125 kilobytes per second. Yes, this is where the trouble starts. On an internet, on a university, I think you can get up to 20 megabits per second on a wireless card, but most of the time you're not, let me tell you. But that means you're at about 12.5 documents per second when you download it, right? And that basically means it would take you about 80,000 seconds to download 1 billion documents, or 900 some days, right? And since we're pretty sure the web is a lot bigger than 1 billion documents, I think the last time Google published a PageRank node count, it was something like 60 trillion links had been found. I think it's in a blog post, and that was some years ago. So it's pretty big. So basically you have this problem, and you have it on both ends. So even if Google buys all the bandwidth in the universe, that when you, I can't speak for Google, but they probably considered it, but no, the real problem is that you have to think about running a web page. And universities have a pretty big internet connection, but if you're a mom and pop store with a perfectly legitimate site, you have to actually pay for the bandwidth that it would take Google to download your pages, because they're being uploaded from wherever your site is hosted, right? So you've got problems on both ends of this, that Google wants to get a lot of stuff at the same time. And particular hosts, I mean, even Amazon, or think about a host like Facebook that has kind of dynamically generated pages, right? Because if you click on your profile, you have one page. If you click on a single post, you have another page. When you do that, you're basically creating a new page. And no major internet service wants to pay for Google to basically suck all of their stuff, even the auto-generated stuff, off of their servers all the time, right? So they're going to pretty much ask you to be polite about that. It's obviously in the interest of someone like Amazon to have their products appear in search engines, but keep in mind you've got multiple search engines also doing all the same thing here. So we can't crawl everything all the time, right? And there's no list of what changes. And this is where everyone says, what about the last modified date? And I'll tell you the only thing that I know about the last modified date is no one ever updates it. So think about that the next time you change a course syllabus or something. Anyway, so despite the fact that Google has a lot of space to store this data, it's really not feasible to just keep a completely replicated copy of the web, even if we had enough space for it. And I would show these pictures because these are actually from an old recruiting talk, but I thought they were funny. So these are the 1997 Google servers. They actually still have a house where they keep the old machines, or at least some reasonable facsimile of the old machines, and they'll show them to you. And this is 2005, I think. This is sort of the first genre that I remember. And they were very secretive about it. And now you can get these great photos. They have a Street View site where you can actually do a walkthrough with the little data center, which is pretty cool. But even if you have space for these petabytes of data that you're going to download, you can't get it, right? So you have to be pretty choosy about what you try to get. I'm just going to give a quick aside because someone always asks, how do you detect an update, right? So humans are pretty good at detecting an update, and there's actually a lot of different ways you can try. I'll show you in a minute. I'm not really going to talk about that except to say there's some interesting statistical problems, and you have to test them on humans and things and look at what a crawler sees. So this page we saw before with the pets, there was actually an ad set in the lower corner that was quietly changing. So you can see it's the lower right corner here. So the content changed, but the ads also changed. And we frequently run into problems that you actually have to detect what we call boilerplate around the edges of a page that changes, but it doesn't really actually change. So there are a couple of, this is kind of what a crawler sees when it sees the page. And you'll see that there's actually functions. So this is what you would see if you went into the View Source tab on your browser. And there's actually functions embedded that are loading ads and things like that. And the crawlers definitely have trouble with trying to filter all this stuff out. So change detection, let me just gloss over it, but basically one of the methods that we use is to sort of fingerprint the page. And that's where the data I'm going to talk about in a minute comes from. So in the top right, what you see is this actually being tested on human raters. So the SIMHASH bit distance is a way of comparing two pages by basically creating a fingerprint of a specific length, like 64 or 96, that is unique to that page. So basically takes a page and usually deterministically will create this random encoding, and then you can compare it. So if the page changes, you'll see that the either letters or numbers or whatever you're doing will have shifted. So it's a really quick way to compare two things, but it's also a very aggregate method. And the graph at the top shows the SIMHASH bit distance goes up to 25, and then the percentage of respondents who agreed in blue that those pages were about the same, and in red that they were a little bit different. And then there's a group that think they're very different, which is not included here. But what you basically see is 0, 1, 2, 3, 4 bits. Most people think they're pretty much the same. But even when you get to 25 bits different, there are still people who think that these pages are basically the same. So it's kind of a challenge to choose a fast aggregate method to actually tell if there's real meaningful content change. So the data we're about to look at uses this method. I think it has a cutoff of 6 bits. And you can see there's kind of like sort of an elbow there. But it's noisy, right? So we see a lot of change that a human would not look at and think that this is like a real change. Now, it might be changes in links that are interesting to the crawler, but that's a whole different topic. So what do we really need to do? Well, it becomes obvious at this point that what we really want to do is look at a page historically and predict what's going to change. Is this page likely to change before I get back to it with the crawler, or should I crawl it faster? So this is where we get to the math bit. So a typical model for the arrival of events, in our case this would be a change to the page, an update to the page, is the Poisson distribution. And this has a lot of uses. I consulted Wikipedia, which is where I get most of my statistical information, because after 10 years at Google, all of my books have disappeared. But you see this infamously in the number of soldiers killed by horse kicks each year in each corps of the Prussian army, where apparently it was very effective. The number of yeast cells used, the number of phone calls, this is the classical probability 101 example, the number of phone calls arriving at a call center within a minute. Internet traffic, I believe this is actually the number of packets that arrive at a queue in any given time increment or something like that. Goals in sports. So you see this all over the place. And this is a typical model for trying to estimate sort of a rate of change. So the Poisson basically says it gives you a probability distribution of the number of events occurring in a specific time interval. It can also be a location, like a square in a field that has seeds deposited on it or something. It assumes, though, that those events occur independently, which is one of the things people question here. And it also implies that the waiting time is distributed exponentially. So the time between an update and the next update should be distributed exponentially. And that's something we can actually check in our particular scenario. Because people are going to ask the question, okay, this would work well in theory, but does it really apply, right? What's going on the internet? So what's going on the internet seems to be that you have people and you have automation. So some pages are, automatically updated at 8 a.m. every day. And some pages are updated whenever you get around to your blog, and some pages are updated once a semester, and there's this whole thing that goes on. So you do see some funny effects. This is a graph showing the percent of changes that occurred in a test sample that we look at to examine whether the Poisson really applies. So in this test sample, we have several advantages. We picked a set of pages which change, on average, in kind of a preview sample, less than 48 hours. So we can get a lot of samples. And then we actually went and fetched them every hour for 2 months. So it had to be someone who didn't mind, but mostly they don't mind. Because this is 30,000 pages in the end, but the initial sample was relatively small. And we managed to get at least 500 contiguous samples for each of the pages that are included here. So we're able to pretty accurately assess when they actually change. The blue line is the change percentage for Chinese, Japanese, and Korean language pages, which are usually in a different time zone. And in red, we have French, Italian, German, and Spanish language pages. And this is done by time of week, although it's in Pacific time because, Google does everything in Pacific time, but you can actually see the offset, right? So FIGS has a very strong and pretty uniform weekly distribution, and then it drops over the weekend. Probably because of the time zone distribution, and also there's some population distribution with people writing in Asian languages in different countries and things like that. You actually see this sort of much jaggier distribution of the CJK languages. And that has a little bit to do with the relative time zones, but it also has a little bit to do with the way the work week, I think, works. That's my speculation. So the thing is, when you look at this data, you do see a certain amount of non-homogeneity in the process that's generating it. The real question is what happens in aggregate. So the graph on the left does show that you get these hotspots. So at the bottom on the x-axis is the average time between changes, and on the y-axis is an aggregation of all the intervals that we observed. So if your average time between changes is 15, you could have a 10 interval, a 20 interval, a 24 interval, a 5 interval, and all of those go into this heat map here. What's interesting about it is that if you look at pages that have an average time between changes over the whole sample of 24 hours, you see there's this horizontal yellow and orange line there. So these are basically cases where pages have more updates arriving exactly 24 hours after the previous update than you would sort of uniformly expect, right? So if a page has an average time between changes of around 24 hours, it's much more likely to have actual time intervals of exactly 24 hours than a sort of random spread. And on the right, we actually have a more statistical, although still a little hand-wavy, test where we use the fact that a Poisson should be generating exponentially distributed inter-arrival times, so the time between changes. And we use a Kolmogorov-Smirnov distance to test whether the arrivals are actually exponential. Now, some of you heard this story earlier, and this is what I was talking about. It turns out that actually using the test is not that effective because we have so many samples for each of these pages that the test typically rejects. This test typically rejects cases just because there's one outlier or something, right? So we have so much data that the test bounds itself are extremely and somewhat artificially narrow. So what we've done here is actually plot the distance. And on the x-axis is the average change interval for the page. And on the y-axis is the distance to the exponential fit. In red, we've colored things that statistically are closer to a 1 hour interval, like fixed 1 hour uniform interval, than they are to an exponential. And in blue, we've colored things that are closer to a fixed 24-hour update cycle than they are to an exponential. And there's always a little stutter here. We may have tried to fetch it exactly on time and didn't get it one time. The page may have been down. We aren't able to assess whether it actually updated. So there's always a little randomness. And there are some cases which say they're closer to a 1 hour interval, but the average change interval is actually longer. And the reason for that is that's typically a case where, for whatever reason, the page didn't update for 2 days or something like that. And that may be webmaster problems, it could be connectivity issues, something like that. So on our previous page, with this sample of really rapidly changing pages, this is actually a significant amount of context. There's about 18% of things in this red block over there, actually. But when you look at it over the whole space of rates of change, about 95% of cases are reasonably approximated by a Poisson. Because there's a whole lot of stuff that isn't changing anywhere near as rapidly as this, and most of it is much more Poisson-like than it is regular. Like, there aren't very many pages that automatically update once a year. There are a lot of pages that are course syllabus that kind of update like once a month or so kind of thing. There's a lot of stuff in that category. So this seems fine. All right, we have our Poisson distribution. So we should be able to do some basic math here, where we observe how often a page has changed. We calculate how long the average time between changes is, and we use the Poisson distribution to estimate the probability that if I crawl this page again C hours later, it has not changed. Yes? This seems fair, right? So this is the probability that the number of arrivals in the interval I've specified is 0. And you get a nice function, which you can do And anyone who's taking, first year probability, you will have that Rice textbook with the Poisson and the exponential and the telephone calls. And you can basically manipulate the equation. So delta is the average time between changes that you've calculated, and C is the crawl interval that you want. And you find out that the probability that the live page matches the page you've got in your index at any time is a function of the ratio of the time between changes and the time you're crawling it on. So if the average time between changes for the page is 2 hours, and you're crawling it every 1 hour, then this is a function of that ratio, okay? So that's great, and this graph looks really nice if you work in a business. You can take a look at it, but it basically says in blue, the expected freshness, that is, that these two pages match as a function of that ratio, and in red it calculates the number of wasted samples, and that's a case where you try to crawl the page and it hasn't changed, so you've just wasted your bandwidth crawling that page. So this seems fantastic, right? This is exactly what we want. This is a decision criterion that we can use. It's pretty straightforward, and we have a small problem. So in the example I just gave you, I crawled those pages deliberately once every hour for a significant period of time. It was a relatively small sample, but the crawler only knows if a page has changed once it visits the page. So even in my sample, I have a problem. I just don't care that much about it. And that is, we have censoring. A page could change every 2 minutes, and I don't know in my sample. So I may be estimating that this page has a rate of changing every 1 hour, but actually the page changes every 30 minutes. So I have a small problem, right? Because in order to actually accurately estimate the delta that was on the previous slide, I would need to sample these pages all the time, which is exactly what I'm trying to avoid doing. So let's start simply. On the top, I have kind of a schematic diagram with the URL and time moving forward to the right. And the blue dots are every time the URL changes. So the page content changes, whatever we're going to talk about changes. In the second line, I have the crawler. And the first crawler moves at an interval, a regular interval of C hours. And the second crawler picks up the page at 2 times C hours. So on the top line, there are 7 actual changes. On the second line, there are 6 changes observed out of 8 intervals, right? Because the crawler only knows if the page has changed when it gets there, and then it can compare the copy it gets to the copy it got last time. And now, in C, option C, which I've overloaded apparently, I have 4 changes observed in 4 intervals. Okay, so the simple estimator we were using basically says that I add up the total number of changes, x, and I divide by the total time. Okay, fair enough, that's what we were using. So what happens? So this says that A, the true frequency is 7 over t, whatever it is. In line B, the estimated frequency of changes is 6 over total time. And in line C, the estimated frequency of changes is, well, I calculated there, but is 4, right? Because I've got 4 observations and I've got the same total time. Yes? Yes. So I have a problem. And this is what we call bias, right? So when you talk about estimators having bias, this is a good example that if we were in a perfectly observed situation where the last modified date told me when the page changed, that this would be fine. But it's obviously not fine because we're not in that situation. So there's a better answer, and it's a simple one, and I'm just going to kind of allude to it here, but this got us into the core of the research problem that I was working on when we did this, which is, okay, so there's a paper, Cho and Garcia Molina, and they derive a simple estimator, which basically says that you want to divide the number of unchanged incidents by the total number of observations, and you want to regularize it a little bit by adding 0.5, or else you're going to get an undefined value. And you want to kind of shrink it a little bit. And this has a significantly reduced bias, particularly if the ratio between your crawl time and your change time is relatively small. So let's look at our tiny example, because this is a good way of saying how this changes things. In light blue, we have the original delta that we estimated using the symbol method. And in darker blue, we have a histogram showing the estimated rates of change we got, the deltas, and it's a histogram, so that's the percent of the sample. And what you primarily see here is that this shifts everything to the left. So in light blue, we thought that there were a bunch of things that changed every 2 hours, but it's much more likely that they actually change every 1 hour. It's just that the averaging effect was glossing over the fact that they were actually changing more rapidly. And when you deal with cases where you have a much longer crawl interval, like 300, the relative shrinkage that you get makes a big difference, right? So 300 might shrink down to like 200, and when you're trying to pick the next crawl interval, that's really important, right? So those types of differences are actually meaningful. So what do you get? Well, this slide's a little incomplete, huh? So when you look at all of the rates of change, on top is a sample of 10,000 pages, and the x-axis is actually done in hours. So all the stuff we've been looking at previously is way over on the left. And there's actually a ton of pages that are way out here and actually max out the scale past 9,000 hours between changes, right? And so this is what we get going through all of this mess with the estimator. And you also see there have been some papers that observed it, that there's differences. So if we look at only high page rank pages, they tend to cluster much more towards the left. So these are like big .com sites, universities, things like that. They actually tend to have a much faster update rate. And there was a paper, I think it's like 2004 federally, where they compare like .com changes much faster than .edu, which I suppose is not surprising. So one of the things you pick up with this when you start to get real resolution is that there are differences. And it actually helps you, and I'm going to sort of close with this, but this is where I entered this particular research problem, was that what we've been looking at before had even crawl intervals. You fetch it every 2 hours, you fetch it every 4 hours, you fetch it however often. In reality, that's never going to happen. Partly because if you're Google, you're queuing these requests. So your queue has a non-deterministic time until you actually issue the request, because you have a certain amount of pipeline going out. And then assuming you're talking to someone else's domain that's also constrained, you may not get your request back as fast as you wanted, or you may not get it this time. So it's really much more realistic that you'll be sampling this page unevenly, right? You'll be getting it this time, then you get a 12-hour interval because something happened, then you get a 2-hour interval, and so forth. So where I came into this research problem was asking the question, how do we pick that interval trajectory going forward? And it turned out there was a paper with a perfectly good solution to this case. It's an MLE estimator, it's not closed form, but it has a key point of undefinition, right? It's undefined when no changes have occurred. Now the problem is, if you're a crawler, most of what you're seeing is new. And what you really want to do, given that you got a new page and you think this page is good, which is a big if, is you want to decide, I just crawled this page, it was just created, what do I do now, right? Because I have virtually no information about it. And one of the reasons I showed you the two graphs before is that, and there's a paper out there you can find on this, what we did is actually use the different prior distributions and find a really cheap way to integrate them into the computation you just saw. Because cheap is very important when you're talking about 1 billion documents. We like cheap. So this is actually where I came into this problem, but I think it's a very interesting problem to talk about, practically speaking, how you can go from something that's pretty straightforward and that's tractable with kind of basic statistics all the way up through something that I'm not even sure we still know the answer to, which is how to choose an optimal path based on this. So where does the problem go, right, just in closing? I mean, how do you identify a meaningful change? The crawler cares about link changes, humans care about the pictures changing. How do you even decide? And that's the part I punted in this talk. What of this is interesting to your search engine and what's not, right? There's a lot of noise here. And then what about pages that go through regime change? The course syllabus is a good example. You change it frequently for a little while, then you start to write out the lecture notes and you change those pretty frequently, and then you basically never change them again, I think, unless you have to teach the class again. So that's a page that doesn't have a steady state rate of updating, so it actually has bursts. And then what about the ideal path? As I just said, we never really closed on the question, what are you actually trying to do, right? Do you want to save more crawl intervals, or do you want to get to the right answer faster? And there's a whole range of answers of what the right strategy is when you're a crawler and you've seen an unknown page. And so this is kind of an open research question, but it's also a very practical one, I think, about what you can do with this type of analysis in a practical setting, and the fact that you're really realizing that we had censoring, and then realizing we need to do something about the censoring, and then realizing that we had uneven intervals, and we got to deal with that, and then realizing that what we want to do is maximize the likelihood, which we're not going to do a billion times empirically, so now we have to do something else. I think that's an example of how you use the stuff that you learn in statistics and in classes to try to empower going forward with some of these problems and knowing when you need to keep going to find the right solution. So that's my talk for today. Hopefully I'm exactly on time.
I'm sure that Dr. Grimes will be able to answer a couple of questions. Okay.
Okay, how much of what you do will be rendered obsolete by the price of web crawling coming down?
So the question was, how much of what we do here will be rendered obsolete by the price coming down? I'm not sure, right? Because A, the price has to come down, and the price always comes down, and the price of storage comes down dramatically. But on the other hand, there's a lot of new content being created that's dynamic. And so you have this race between something like Twitter, which is just generating tons of stuff. You can search for all these hashtags, and each one of those is like a page. Maybe that should be dealt with in a structured way, but there's different options. But you also have the fact that places like India are really developing a much more, you saw that graph, and English like just sucked the whole thing in. But now, you're really seeing presence in a lot of different top-level domains. You're really seeing presence in countries that don't have, like some countries physically do not have the connections to the internet that we have in the US. So even if your home connection gets better, it's still a challenge to try to ship data like wholesale in and out. And I think there's a lot of really interesting web development going on in places that don't have as much infrastructure, and that's going to keep limiting some of the options in terms of crawling. And of course, that's where you want to get the content, because the content's growing really fast. But yeah, I think there's a day when like the whole web is just structured feeds that move around, and like everyone knows when anything gets updated, and it's just fed to you if you're interested in it. I think that's a possibility. I'm not sure we can ever crawl all of it as fast as it grows.
Question way in the back there.
This doesn't really have to do too much with the presentation, but will Google Fiber ever come to Minnesota?
I really don't know. I hope so, because I've been asked that twice. But yeah.
Just two questions. Question number one is, have you tested this approach on some place where you actually know how frequently things are updated, like Wikipedia, for example? You can question, it has the same structure like the web. It's approximation, of course, but you know the actual changes.
Yeah, it actually, it doesn't work too badly, I'll say that. You know, but the thing is, like, if you look at these probability distributions, in aggregate, it doesn't work too badly. But even these likelihoods of change, I mean, because the Poisson is an actual distribution, the reality is, like, you've got to crawl this page still much faster than it changes on average to be really confident that it didn't change, right? There's always some probability that it already changed within 5 minutes, even if you think that it changes every 24 hours. And unfortunately, for people trying to crawl the web, that appears to be very true.
And that leads to my second question. Is how short do you want the interval? If the web page is updated every half a second, do you really want to get every single update here? Or maybe it's not important because humans would not see it anyway?
Yeah. So
What's the time limit that you want? How short could it be?
So, I mean, I have two answers to that. One is, I don't think there's a perfect way right now to determine what updates we want, right? Because the crawler wants link updates, but the reality is if you show them to people, most people don't notice, right? And then a lot of the link updates, and there was some of this quietly in this presentation, are not meaningful. Like, they're the same links just being recycled over and over again, so they're not actually new. So there's a lot of noise that's generated by that I think needs better solutions. And if you look at the literature, there's like shingle methods and like overlapping there's all kinds of methods for trying to deal with that. But the answer, you know, one of my colleagues has is that this is really an optimization problem. You look at how badly you want the page, whether it's the quality signal, how often you're going to show it to people, and you assign that a cost. And then you assign a cost to your crawl based on, I don't know, the limit on that particular host or based on your outgoing bandwidth, and you basically solve the problem. And you can get a pretty neat solution depending on what your costs are. But I don't know if it's the right solution because of this whole, you know, there's a lot of noise in this problem. And we're trying to be better because better counts at this scale. I don't think it's right. But better is worth a lot when you're talking about this many pages.
Okay, I think we'll end here. Thank you very much for coming.